Welcome to this walkthrough of LeetCode problem number 916, word subsets. In this problem, we'll explore a fascinating challenge involving universal strings and subsets. By the end of this session, you'll have a clear understanding of the approach and how to apply it to similar problems. Let's dive in. In this problem, you are given two string arrays, words 1 and words 2. The goal is to determine which strings from words 1 are considered universal strings. A string B is a subset of a string A if every letter in B occurs in A at least as many times. For example, the string WRR is a subset of warrior because warrior contains all the letters in WRR with the required frequencies, but WRR is not a subset of world because world does not contain two Rs. A universal string in words 1 is one that satisfies the subset condition for every string in words 2. In other words, each universal string must contain all the required letters from words 2 and the necessary frequencies. Your task is to return a list of these universal strings from words 1, and the order of the strings in the output does not matter. The input size constraints are also provided, with words 1 containing up to 10,000 strings and words 2 containing up to 1,000 strings. Each string in the arrays consists of lowercase English letters only, and the length of these strings is at most 10 characters. Let's look at an example to understand the problem better. Here, words 1 contains the strings Amazon, Apple, Facebook, Google, and LeetCode, and words 2 contains the strings E and O. To determine the universal strings, we check which strings in words 1 meet the requirements specified by words 2. Specifically, each universal string must have at least one E and at least one O. For instance, Facebook is universal because it contains one E and one O. Similarly, Google qualifies because it has one E and two O's, which satisfies the subset condition. And LeetCode is universal because it contains two E's and one O. These three strings meet the requirements of words 2 and are included in the output. On the other hand, not all strings in words 1 meet these requirements. For example, Amazon does not contain any O, and Apple does not contain any O either. Therefore, they are excluded from the output. Now, let's consider another example. Here, words 1 remains the same, but words 2 contains the strings L and E. This means that any universal string must have at least one L and one E. Apple satisfies this because it contains one L and one E, so it is included in the output. Similarly, Google qualifies because it has one L and one E. LeetCode also satisfies these conditions because it contains one L and two E's, so it is included as well. However, Amazon and Facebook are excluded because they do not meet all the requirements of words 2. For our final example, let's change words 2 to contain the strings O and E. This means that any universal string must have at least one E and at least two O's. Let's see how this affects words 1. Google is the only string that satisfies these requirements because it contains one E and two O's. None of the other strings in words 1 meet the conditions, so they are excluded from the output. Finally, let's briefly discuss some edge cases. If words 2 is empty, then all strings in words 1 are considered universal because there are no constraints to satisfy. On the other hand, if words 2 contains a string with all 26 letters, only strings in words 1 containing every letter will qualify. Additionally, when words 2 has strings with duplicate letters, such as AA or BBB, the universal strings must meet the highest frequency of each letter across all strings in words 2. These scenarios help clarify how the problem can vary based on the input. To tackle the word subsets problem, our goal is to determine which strings in words 1 qualify as universal strings, meaning they are supersets of all strings in words 2. One approach we could consider is the brute force method. The intuition behind this approach is straightforward. For every string in words 1, we check whether it satisfies the requirements of all strings in words 2. To do this, we first calculate the frequency of each character in both words 1 and words 2. Then, for every pair of strings, we compare their frequency maps to determine if the string from words 1 contains all the characters of the string from words 2 in sufficient quantities. If it does, we include it in the result. However, this approach has a significant computational cost. Calculating frequency maps for all strings takes time proportional to their combined lengths, while checking all pairs of strings involves a nested loop, making it expensive as the input size grows. The total time complexity ends up being proportional to the product of the sizes of words 1 and words 2, multiplied by the maximum string length, which is inefficient for larger inputs. While the brute force approach is simple to implement, it has notable drawbacks. One major issue is its inefficiency, as overlapping character requirements in words 2 lead to numerous redundant checks. To address this, we consider an optimized approach that builds on key observations about the problem. Instead of comparing each word in words 2 against every word in words 1, we can aggregate the character requirements from all strings in words 2 into a single frequency map, called max_frequency. This map tracks the highest frequency of each character across all strings in words 2, so we only need to perform one comparison per character. The intuition here is that a string from words 1 is universal if and only if it meets the maximum frequency requirements for all characters in max_frequency. By pre-computing max_frequency, we eliminate redundant computations during the comparison step. The process involves two main steps. First, calculating max_frequency by iterating through all strings in words 2 and updating the map with the maximum frequencies of each character. Then, for each string in words 1, we check if its frequency map satisfies the requirements in max_frequency. If it does, we include it in the result. The optimized approach offers a significant improvement in efficiency. Pre-computing the max_frequency map requires iterating over all strings in words 2, which takes time proportional to the product of the number of strings and their average length. Checking each string in words 1 against max_frequency involves a similar process, taking time proportional to the product of the number of strings in words 1 and their average length. When we combine both steps, the overall time complexity becomes linear relative to the total input size, specifically O, n2 times L2 plus n1 times L1. This is a substantial improvement over the brute force approach, especially for larger inputs. However, the trade-off is a slight increase in memory usage due to the additional storage required for the max_frequency map. Despite this, the memory overhead is minimal, especially when compared to the performance gains. By avoiding redundant checks and aggregating the requirements into a single map, we achieve a much more scalable solution for the problem. Given these considerations, we chose the optimized approach for its balance of clarity and efficiency. Pre-computing the max_frequency map minimizes redundant operations and makes the solution highly scalable, as each string in words 1 only needs to be compared against a single aggregated set of requirements. This is particularly advantageous for larger inputs, where the number of strings and their lengths can grow significantly. The brute force approach, on the other hand, becomes impractical for such cases due to its repetitive subset checks and high computational cost. The optimized approach not only reduces computation time but also simplifies the implementation once the aggregation step is understood. While it does use slightly more memory to store the max_frequency map, this trade-off is negligible when weighed against the substantial performance improvements. Overall, the optimized approach is the most practical and efficient solution for solving the word subsets problem, especially when working with large-scale datasets. In the word subsets problem, the goal is to identify which words in the words 1 list are universal strings. A word is considered universal if it contains all the characters, with at least the required frequency, from every string in the words 2 list. For example, if words 1 contains words like Amazon, Apple, Facebook, Google, and LeetCode, and words 2 contains the strings E and OO, the universal words would be Facebook, Google, and LeetCode because these words meet the character frequency requirements derived from words 2. To solve this problem efficiently, we need to treat it as a superset comparison. Each word in words 1 must be a superset of all the strings in words 2. Instead of performing this check for every pair of strings, we can pre-process words 2 to compute a combined frequency requirement for all its strings, which simplifies the process significantly. To pre-process the words 2 list, we compute a combined frequency requirement across all its words. First, we create a max_frequency array of size 26 to represent the maximum frequency required for each letter from A to Z. Then, for every word in words 2, we calculate its character frequency using a helper function called count_frequency. This function generates an array of size 26, where each index corresponds to a character's frequency. We then update the max_frequency array by taking the maximum frequency of each character across all words in words 2. This way, the max_frequency array becomes a consolidated requirement that every word in words 1 must meet to be considered universal. Next, we filter words 1 by iterating over its words, calculating their character frequencies, and comparing them with max_frequency. If a word meets or exceeds the required frequency for all characters, it is added to the result list, which contains the universal words. Pre-processing words 2 into a single max_frequency array is a key optimization in this algorithm. Instead of redundantly comparing every word in words 2 against each word in words 1, we consolidate the requirements into a single array, which significantly reduces the computational complexity. The use of frequency arrays is particularly efficient here. By leveraging an array of size 26 to represent character frequencies, we ensure that operations like comparisons and updates are performed in constant time for each character. Additionally, while verifying if a word in words 1 satisfies the max_frequency requirements, we can exit the check early as soon as we find a character whose frequency is insufficient. This early exit further improves performance by avoiding unnecessary computations. The algorithm also relies on two main data structures: the frequency array, which is space efficient at a constant size, and the result list, which dynamically stores the universal words. Together, these structures ensure the solution is both time efficient and space efficient. Analyzing the algorithm's complexity reveals its efficiency. For the time complexity, computing the max_frequency array involves iterating through words 2 and calculating character frequencies for each word. This takes n*k, where n is the number of words in words 2 and k is the average word length. Filtering words 1 involves a similar process. For each word in words 1, we calculate its frequency and compare it with max_frequency, resulting in m*k, where m is the number of words in words 1. Combining these steps, the overall time complexity is n*k plus m*k. For space complexity, the frequency arrays used for words 2 and words 1 are constant in size, requiring 1 space. The result list's space usage depends on the number of universal words, which is m in the worst case. Together, these complexities demonstrate that the algorithm is well suited for handling larger inputs efficiently. Now, let's break down the core implementation using pseudocode. The implementation begins with the helper function count_frequency, which takes a word and computes its frequency array. For the main function, we first calculate the max_frequency array by iterating over each word in words 2 and updating the maximum frequency for each character. Then, we filter words 1 based on these requirements. For each word in words 1, we calculate its frequency and check if it meets or exceeds the max_frequency requirements for all characters. This check uses a simple condition: if every character's frequency in the word is greater than or equal to the corresponding value in max_frequency, the word is added to the result list. Finally, we return the result list containing all universal words. This straightforward approach, based on pre-processing and efficient frequency comparisons, ensures that the solution is both concise and optimal for solving the problem. The provided solution implements the word subsets problem using Python. 1. Importing libraries. The collections counter module is imported to count the frequency of characters and strings efficiently. 2. Defining the function. The word subsets method takes two inputs: words 1, list of candidate words, and words 2, list of constraints. 3. Calculating maximum frequencies. The first step involves determining the maximum frequency of each character across all words in words 2. A counter object, max_frequency, is used to store these maximum frequencies. For each word in words 2, the character frequencies are counted using counter, and the maximum frequency for each character is updated in max_frequency using max. For filtering candidate words, the second step filters the words in words 1 to find those that meet the universal condition. For each word in words 1, its character frequency is computed using counter. The word is added to the result list universal_words only if it contains all characters from max_frequency with at least the required frequency. This is checked using a generator expression inside the all function. 5. Returning the result. The filtered list of universal words is returned as the output. ###complexity analysis. Time complexity. Let n be the total characters in words 1 and m be the total characters in words 2. The complexity of counting characters in each word is linear, so the time complexity is n plus m. Space complexity. The space required is k, where k is the number of unique characters across all words in words 2. This implementation is efficient and adheres to the problem constraints, ensuring correctness and optimal performance. Here, we start by defining the word subsets method, which takes two arrays of strings, words 1 and words 2. The goal is to determine which words from words 1 are universal with respect to words 2. To do this, we first need to calculate the maximum frequency of each character across all words in words 2. This is done using the max frequency array, where each index represents a letter from A to Z. For every word in words 2, we call a helper method, countFrequencies, to compute the character frequencies for that word. Then, we update max frequency by taking the maximum value for each character index. After combining the character requirements from words 2, we move on to filtering words 1. For each word in words 1, we again compute its character frequencies and compare them against max frequency. If any character frequency in the word is less than the required maximum, we mark it as not universal. Otherwise, if it satisfies the universal condition, we add it to the universal words list. Once all words in words 1 have been checked, the method returns the universal words list, which contains all the universal words that meet the criteria. To support the above logic, we use a helper method called countFrequencies. This method takes a single word as input and creates an array of size 26 to represent the frequency of each letter from A to Z. By iterating through the characters of the word, we increment the corresponding index in the frequency array based on the character's ASCII value. This simple utility makes it easy to compute and compare character frequencies efficiently. With these components in place, the solution is structured to handle the problem requirements effectively while maintaining clarity and modularity in the code. To solve the word subsets problem, we start by analyzing the inputs. Here, words 1 is a list of potential universal words, and words 2 contains the constraints that any universal word must satisfy. First, we build the max_frequency counter from words 2. This counter keeps track of the maximum frequency of each letter across all words in words 2. For the word E, we update max_frequency to include 1E. Similarly, for the word O, we add it to max_frequency, resulting in counter E1O1. With max_frequency built, we filter the words in words 1. For each word, like Amazon, we count its letters and check if it satisfies the frequency constraints in max_frequency. Amazon is missing an E, so it's not universal. For Apple, it fails because it doesn't meet the requirement for O. However, Facebook satisfies both constraints, so it's added to the universal words list. Next, we check the remaining words in words 1. The word Google has the required counts for both E and O, so it qualifies as universal. Similarly, LeetCode also meets the constraints. After evaluating all the words, the final list of universal words is Facebook, Google, LeetCode, which is returned as the output for this example. Now, let's look at an edge case where words 2 is empty. Since there are no constraints, the max_frequency counter remains empty. This means that every word in words 1 automatically qualifies as universal, as there are no required letter frequencies to satisfy. With no constraints in words 2, we proceed to filter the words in words 1. For each word, like A, B, and C, we calculate their letter frequencies. Since there are no constraints to check against, each word is considered universal. As a result, the final list of universal words is simply all the words from words 1, which are A, B, C. This demonstrates that when words 2 is empty, the solution simplifies to returning all words in words 1. Now, let's explore a more complex example with multiple constraints in words 2. Here, the input includes constraints for the letters A, N, and E, each requiring a frequency of at least 1. We begin this example by building the max_frequency counter from words 2. For A, we add it to max_frequency with a frequency of 1. Similarly, for N and E, we update the counter to include those letters, resulting in counter of 1, N, 1, E, 1. With max_frequency constructed, we filter the words in words 1. The word orange meets all the constraints, as it contains at least one A, N, and E, so it's added to the universal words list. However, banana lacks the letter E, and grape is missing N, so neither qualifies as universal. The final result is orange, which is returned as the output for this example. This illustrates how the constraints in words 2 shape the filtering process to determine the universal words. In evaluating the time complexity of our solution, we break it down into two main phases: building the maximum frequency map for words 2 and filtering words 1 based on the universal condition. First, let's look at building the maximum frequency map for words 2. Here, we iterate through each word in words 2, and for each word, we calculate its character frequency using the counter class. This step takes time proportional to the average length of the word, which is L_2. Since there are m words in words 2, the total time for this phase becomes M*L_2. Additionally, as we update the maximum frequency map, we only deal with a fixed set of 26 lowercase letters, making these updates constant time operations. Now, moving to filtering words 1, we follow a similar process. For each word in words 1, computing its character frequency also takes L_1, where L_1 is the average word length in words 1. To check if a word satisfies the universal condition, we compare it against the maximum frequency map, which involves fixed constant time operations proportional to 26 letters. This makes the time for checking each word 1. Repeating this for all n words in words 1 results in a total time complexity for this phase of n*L_1. When combining the time complexities of both phases, we get the total time complexity of the solution is M*L_2 for building the maximum frequency map and n*L_1 for filtering words 1. Adding these together, the overall time complexity becomes M*L_2 plus n*L_1. To understand this better, in the worst-case scenario, m and n represent the total number of words in words 2 and words 1, respectively, while L_2 and L_1 represent the maximum lengths of words in their respective lists. This combined complexity ensures that our solution scales efficiently with respect to both the input size and the word lengths. Now let's turn to the space complexity. In the first phase, where we build the maximum frequency map, each word in words 2 requires a counter object. Since we're only counting lowercase English letters, each counter uses 26, or effectively 1, space. The maximum frequency map itself also stores at most 26 entries, so its space usage is 1. In the second phase, when filtering words 1, each word again requires a counter object, which similarly takes 26, or 1, space. However, the list universal_words accumulates all the words from words 1 that satisfy the universal condition. In the worst case, every word in words 1 might meet the condition, meaning the total space required by this list is proportional to the combined length of all words in words 1, yielding a space complexity of n*L_1. Combining these observations, the dominant factor in space usage is the universal_words list, so the overall space complexity of the solution is n*L_1. Analyzing the performance further, let's consider best, average, and worst-case scenarios. In the best case, if words 2 is empty, there's no need to filter words 1, and the time complexity reduces to just the cost of building the maximum frequency map, M*L_2. In the average and worst cases, both phases are fully executed, resulting in the full time complexity of M*L_2 plus n*L_1. To appreciate the efficiency of this approach, we can compare it with a brute force solution. A naive approach would involve comparing every word in words 1 with every word in words 2, checking character frequencies for each pair. This would result in a time complexity of n*M*max L_1, L_2, which is significantly worse than our optimized solution. Furthermore, the brute force approach could achieve 1 space complexity if no frequency maps are stored, but this comes at the cost of much higher runtime. By pre-computing the maximum frequency map for words 2, our optimized solution avoids the need for nested iterations, achieving far better efficiency, especially when n and m are large. Finally, let's solidify our understanding with a mathematical justification for the solution's efficiency. The use of counter ensures that counting characters in a word is linear with respect to its length, L. The comparison against the maximum frequency map is bounded by the fixed set of 26 lowercase letters, making it a constant time operation, 1. By processing words 1 and words 2 in a linear fashion, the runtime scales directly with the total size of the input, specifically O, M*L_2 plus N*L_1. This combination of linear scans and constant time operations ensures that the solution achieves optimal performance within the constraints of the problem, making it both time efficient and space efficient for handling large inputs. One of the most common mistakes in solving the word subsets problem is not pre-computing the maximum frequency for words 2. Instead, some may directly compare each word in words 1 with every word in words 2, which leads to redundant computations and significantly increases the time complexity. To address this, it's essential to create a frequency map that stores the maximum frequency of each character across all words in words 2. Another frequent issue is calculating frequencies incorrectly. If you reuse the same frequency map for all words in words 1 without resetting it, the frequencies will accumulate and lead to inaccurate results. The solution here is to either use a fresh map for each word or clear the map after each comparison. Additionally, ignoring edge cases like empty input lists or strings with no characters can result in errors or incorrect outputs. A good practice is to add explicit checks for these scenarios at the start of your solution to handle them gracefully. Another inefficiency arises when you compare every character in words 1 directly against words 2 without leveraging the pre-computed maximum frequencies. This approach results in unnecessary operations and slows down the solution. By using the maximum frequency map, you can streamline the process to a single comparison per word in words 1. Overcomplicating the solution is another pitfall to avoid. While data structures like tries might seem appealing, they aren't necessary here and can make the implementation needlessly complex. Instead, sticking to the frequency map approach keeps the solution both efficient and easy to maintain. This problem offers several insights that are valuable in an interview setting. First, it involves recognizing patterns of subsets and supersets, which is a theme commonly encountered in string-based problems. Identifying this early can help you structure your approach more effectively. Efficiency is also key to highlighting how you reduce redundant computations by pre-computing the maximum frequency map for words 2 demonstrates optimization skills. Be sure to address edge cases explicitly, such as handling empty inputs or very long strings, as this shows careful consideration of problem constraints. You might also want to discuss spacetime trade-offs, emphasizing how the use of extra space for the frequency map significantly improves comparison efficiency. Finally, modularizing your solution into clear steps, like pre-computing the frequency map and then processing words 1, helps convey your thought process in an organized and logical manner. This problem shares similarities with several other LeetCode problems, making it a great opportunity to draw connections. For instance, in LeetCode number 49, Group Anagrams, you use character frequency counts to group words with the same characters. LeetCode number 438, Find all anagrams in a string, also involves character frequencies, but it incorporates a sliding window technique. LeetCode number 242, Valid Anagram, focuses on comparing frequency maps for 2 strings, which is directly applicable to the word subsets problem. Finally, LeetCode number 500, Keyboard Row, is another string processing problem with simpler constraints, which can serve as a good warm-up exercise. There are alternative approaches to solving this problem, though they vary in efficiency and complexity. The brute force approach, for example, involves comparing each word in words 1 with every word in words 2. While simple to implement, it's highly inefficient and only suitable for very small input sizes due to its N*M*K time complexity. A more advanced but less intuitive method is bit masking, where you represent character occurrences with bit masks and use bitwise operations to check subset relationships. This can potentially reduce space usage but comes at the cost of increased implementation complexity. Another option is a tree-based solution, where you build a tree for words 2 and check each word in words 1 against it. However, for this specific problem, tries add unnecessary complexity and are typically slower than the frequency map approach. Great job following along. To summarize, we tackled word subsets using a frequency-based approach, optimizing for both time and space complexity. Key takeaways include understanding universal strings and leveraging frequency arrays for efficient comparisons. Thanks for watching, and don't forget to like and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!